Does that appear large enough on everyone's screens, or is the text a bit small? Hmm. Okay.
And browsers.
In the browser as well. Yeah. Good. Okay, so welcome to the second interactive part of the tutorials today. We're taking a bit of a step back in the process of analyzing the simulated data to look at actually building the detector and building the detector and running a couple of simple simulations and changing a few parameters to see how that affects the detector that we're building. So we'll start with just how the detector is defined and move on to actually visualizing it, and then going into actually creating a new detector or modifying the detector that's already there. So there's a brief introduction here. Won't read it out, but it's basically why we're using DD4HEP from my perspective is that it's a package which connects a lot of different components together and builds on top of them, including obviously root and geomp4, which are sort of the two main pillars of high-energy physics computing. It also allows you to output into modern formats, and it is being developed as we go along. So any problems that we run into, there are always developers who we can contact to get new things put in. Right. So the geometries, so a detector is installed on the EIC shell by default. So if we go into the EIC shell, I'm already in there, so I'll just leave. I'm actually working on a remote machine today, so there hopefully aren't going to be any problems, but there might be. Oops. So in EIC shell, you've got a number of different geometries from historical builds, mostly for the simulation campaigns. As they release a new release, they update the containers geometries. So here we've got, can go back in time, only back to October last year. There'll be some conflicts and compatibility issues beyond there with the EIC show, I believe. So they remove older versions and you've got the newer versions. But if you want to work with what has been most recently pushed to the GitHub repository within the last 24 hours, then you need to work with this epic nightly directory. So inside there, you can copy this and look inside there and see that we've got these folders. The most important thing for this is the setup script, which sources all of the relevant paths to the environment so that we can run a simulation with that particular epic nightly detector setup. So source that, and it moves into this, changes the shell a bit here and includes this nightly tag at the start. So we can look inside here, investigating new environment variables that have been now defined, so that internally, when you run the simulation, it knows where to look to find different configuration paths. So if you can normally run env, which shows you all of the environment variables. But if you do, they do this later? No. Env, and then you now can grep for detector, and it will come out with these paths that have now been set. So detector path, detector config, detector version, and the name of the configuration that you're wanting to use now. So very first exercise here is just to make sure that you can do that yourself. So go into the EAC shell and source this nightly detector setup, which is the same as the main detector setup, and then try again with a different detector setup from a previous release. So one of the dated releases in the opt detector directory, and check that these change when you source the other path. Just give a couple of minutes for anyone to check that, and if anyone's got any problems loading anything, please speak up or add it to the Mattermost chat, because don't want to leave anyone behind. Sure. Close that chat. So what I've got here is this isn't working on my machine. This is a machine in Glasgow, which is VS Code is SSH'd into. Sorry? So, yeah. Or minus some. Good. Because I worked on that. Didn't work. Yeah, so the VS Code shell is on my machine in Glasgow. It simplifies some of the details. I tend not to actually work on this laptop. I normally work elsewhere, and yeah. So some of the visualization stuff that we're going to look at in the next stage is all going to be. You can do that on any machine. That's just through a browser if you've got the right file. Okay, so hopefully everyone's managed to do that. Relatively simple task. Now, next step, just look inside this detector path. I'll go back to the sourcing the. I'm going to hide this. Sourcing the nightly one, and then look inside ls detector path. This has a bunch of different XML configurations which we can choose. So these are all top-level XML files which describe a detector that you might want to do some studies on. So the main one here is the epic.xml, which is the one used for most of our campaigns. And if you're looking to do physics analysis with the whole detector, you'll probably want to use that. There are some additional ones, for instance, the ones tagged with different beam energies. If you're not using, I believe, just double check which beam energy is so this is the epic.xml. You need to change the beam energies within this if you're wanting to. Well, yes, yeah. So each of these has a different beam energy, or if you want to change the beam energy. So this is epic.xml appears to just have 5 by 41, which might not be what you want to run with. So in which case you'd have to change to 18 by 275 or 10 by 275, or if you've got a very specific use case, then you'll have to create a new entry in the YAML file and new configuration paths, but not going to go into that at this point. So yeah, you can look inside this either using less or any editor that you like. The default here, as given by the previous, looking at this one, the default was just the epic. So we can look inside this using less, or I've already opened it in a browser above here, so I can just look at it using the VS Code browser. We'll go through this just a bit. There's some details at the top. These are some defines, so these are defining some constants which are relevant to different bits of the detector. And then some GDML properties, and then go down a bit further and we get to our detectors. So here we've got all of the definitions inside each of these paths, sub bits of detectors which are describing different components and how to build each of your detectors within these. So I suggest we look inside this, just the vertex barrel tracker, just to have an example. I've already opened this one, the paths on the right here, and we can see here, need to zoom out a bit to see more of it, make it too small for everyone. It's got a bunch of constants defined at the top, which are usually defined based on other constants which were previously defined in the define.xml or some step which has been included before this particular XML is loaded. Then it's got a huge list of constants here, and a small subset on the right in the tutorial window. And then where the sort of more heavy lifting, which DD4HEP needs in order to build its detectors, is in this detectors block. So here you've got an ID for the detector so that it can be located, a specific name, and then this type, readout, and some various other parameters which are being defined either within the code or are native to the DD4HEP properties that it's expecting. So yeah, you can go have a look through this, find a different subsystem that you're interested in, and try and work through how that is built, where to get, if there's a specific path from the epic.xml that you need to take in order to get to that, and where all of the parameters that you might be interested in are defined. yeah, just give you another couple of minutes to have a look around and see if you can pick out any, for instance, anything which is text in here has to have a value defined somewhere within the XML chain. So if you want to find out where vertex barrel layer 1 min is defined, you have to go back to here and then back to what this was defined as, and this is defined outside of this particular file, but it's defined as a subtraction of two different constants there. If anyone gets lost, yeah, speak up again. Yep.
So this type is starting this epic. Remove this epic first, and then find this file, for example, vertex barrel.c.
So the easiest way to, that's part of. Sorry, I will repeat my questions here. So this type epic vertex barrel, you should remove the epic prefix and find this vertex barrel.c file somewhere in the compact configurations. If I want to know where the volumes created. If you want to know where these are actually created, that's a couple of steps ahead, but that is the key, sort of connecting the source file to the XML file is this this type here. I would recommend, if you want to, they won't necessarily be named correctly, so there might not be a vertex barrel.c or epic underscore vertex barrel.c, but you should go into the source directory and grep for epic underscore vertex barrel, and it will find the .c file that creates that actually, yeah, contains the code to create that. I've got that. That's part of the next, maybe the next tutorial or next step. Yeah, okay, so we'll move on to that hopefully now, or maybe, yeah, I think that's 2 steps ahead actually. Okay, if anyone's, again, lost or wants to speak up, let me know, but I'll move on to the geometry now that we've had a couple more minutes there viewing the geometry. So a number of different ways to do this. The way that we've previously shown it is this DD web display, and I'm going to focus mostly on that with a little bit of just viewing it straight in the Geomp4 GUI. And then there are other things that you might want to think about, the ACT surfaces and ACTS surfaces and the material maps and an event display eventually, but these aren't included in this tutorial. So start by looking at just the main detector configuration. So I'm not sure what, I didn't check this. Has everyone got this EIC directory from the previous tutorial, or? Yes, no? Okay, so it doesn't necessarily matter where you are to do this. So wherever you've got your EIC shell, or in theory anywhere, and then yeah, so DD4HEP X is based on this root TGO format, and in order to view that, root has some quite nice visualizing. The JS root visualizer does a good job of showing us displaying this TGO format. So DD4HEP provide this converter. So we have already sourced the detector geometry. We can just now paste in, export this geometry, and it will take a little while because it's building the geometry with all of the C code and the XML links, and then after that it should have produced this detector geometry.root file. We can view this either using this either of these. These are the EIC app Argon JS root install, or the slightly more up-to-date Cern version. This is where my working remotely comes a bit problematic. Hopefully I've got a version of a geometry previously exported here. So you can load it in, select it in wherever you exported it, select it in your window here, and then, and then if you right click on default, you can do draw all. It might take a while, it's drawing. Okay, so this particular one was a different geometry setup. So it has no central detector. It's just got the far forwards, far backwards regions, and the middle there. One of the nice, useful interesting things I found with VS Code is it's got this nice extension where you can actually just use the root, JS root viewer. So I can find the one that I just created here, and load that one in just to the VS shell here. So it's almost identical to the browser. Can just draw all. Again, takes a couple of seconds. Lots more shapes to build in the full geometry than the just far forwards and far backwards. And this is actually loading it remotely, so it takes probably a bit longer, but it's really quite fast. Once it's loaded into the browser, it's
Can I ask a question? What is the maximum of the elements displayed in this browser? Is there a maximum?
I'm not sure.
Okay.
It tends to, I think it theoretically limits it.
There is a limit. I don't know exactly what it is, but in drawing the luminosity spec parameter, it's simply fiber with lots of individual fibers, and if you try and draw the whole thing in, there is some limit on the order of coming through.
So the answer is there is a limit.
There is a. You could probably change the limit if you're desperate. So here we've got the central detector, far backwards region this way, far forwards region that way. What's nice here is that we can now toggle the UI browser, and we can, for instance, clip in X and Y at 90 degrees, and then it will show us some of the internal structure, which is currently hidden by the then we can additionally, if you right click on anything in particular, if you want to zoom in, where's it gone? So we want to focus on a particular bit. So this here it's hovered over the end cap. So, it's going slowly because it's running remotely, not because it's a big geometry. Okay, we'll go back to this one to demonstrate. If you want to focus on a particular element here, hover over it, and then you can zoom in, and it will zoom in, show you which bit of the detector you want to look at, and then you can rotate, zoom in, zoom out. You can see inside here, there's the B0 detector. This might be an old version of it, and then the 0 degree calorimeter down there. You can hide bits, turn them into wireframes. So turn the magnet there into a wireframe if you want to look inside it. Right click moves around, whereas left click normally pans around. Yeah. Then you can hide components if you don't want to see them, or focus in on them. Yeah. Right. Back to so if you want to look at a slightly different geometry than the whole one, then you should locate a different path here. I think I need to refresh this. It's cached. No, it's just not updated. Okay, so here, for instance, this is the geometry that I was just looking at, the just IP6 geometry, which extends forwards and backwards and includes the central beam pipe, but doesn't include any of the central detectors. If you choose one of the different geometries that we were looking at up above, so these PF rich only or imaging only, and then you can just export that. If you wanted to export it as a different name, you use this -O flag. Then if you don't have access to a browser for whatever reason, you can do this internally using sort of the root T browser GUI. You just calling these two commands within your root command line.
It can look different depending on what you do. It may look nicer. Or
You got it nicer? Okay.
It also depends on your browser version. Different depending on how new or old your
Okay. How new or old your root version is compared with your JS root version compared with, okay.
I mean, if you have a local root installed, give it a shot. If you don't, then don't. Yeah, exactly. It's not root 7 yet, it's using browser.
Yeah. So if I go into here, I can try that directly. So if you load up root, this is going to be tiny, isn't it? It's always tiny no matter what screen I show that one on. And then copy. Pasting is always different in different. So that's loading the geometry, and then you can draw it. Yeah, that looks very different. What was? Maybe it's just got these extra boxes for.
But if you want to like really customize how it's displayed, like with colors and all kinds of stuff, you have to kind of start from the browser is nice, but it's just for looking at it quick. You want to do detailed work, you need to do this kind of approach. It's just
Yep. Okay. Yeah, so the exercise is just to do this yourself. If you haven't already, do this for one or two different geometry setups, configurations, and yeah, view it in your geometry viewer of choice. And then just compare the two, see what's implemented in in any particular configuration. Yeah, if anyone has any problems running any of these different methods, that let us know. Okay, so yeah, the other type of visualization, which is incredibly useful for debugging your simulation while it's running, is actually the Geom4 visualizer. This is, for various reasons, this might not work. I've had problems with the X window forwarding out of the EIC shell onto my machine. I don't know if anyone else struggles with this, but particularly prior to, well, in other simulations, other projects, I've used this extensively for sort of debugging where tracks are going and actually visualizing that side of things rather than just looking at the geometry. So I've discovered that I can do it just through SSH forwarding, and it works fine out of the EIC shell. So I can give a quick demonstration of that. Here we need to actually run the simulation with this run type Qt, which brings up the GUI, Geom4 GUI. Would suggest here not using the IP6. I tried to change this a second ago, using something like the vertex only.xml, as it's a much smaller configuration. And then here we're feeding in an input file, which is a remote input file from the xrootd server, and then the macro is just this defines how this is being visualized. It's a Geom4 macro. You can, if you're familiar with Geom4 macros in any way, you can stick anything in there, but this is the one that's normally used as a default for these things. So this macro should be in the EIC. Oh no, wait. It's in the source code for the Epic repository. Is it in the EIC shell as well? It might not be. We might need to delay this until the next. Yeah, something I haven't considered. So this macro can be it's pretty much in almost every Geom4 geometry that's used. This macro exists, but we can delay this until after you've pulled the Epic repository into a new directory, and then run this separately. But what you get is this nice, this is exported, so it might take a while to update, but this nice, in this case, this is the 3 inner vertex tracking layers, which are being given these, fed these events from this particular file. And then if you press beam on, it feeds the next event. You can see electron coming in one way, proton coming in the other. Oh no, the electron going out one way and the proton going out the other, and a spray of particles. You can again turn the trajectories on and off to just look at the geometry, and then look at individual components of the geometry. So you can hide those, or yeah, hide individual layers, hide individual modules with that. With the full geometry, it's not so useful. If you send in an event, unless you're looking at a very particular region, it's a huge spray of mostly gammas, which mean that you can't see the geometry behind this all of these tracks anymore unless you turn the trajectories off, and it's much slower to visualize than just using the T-root geo. So if you're looking at the geometry itself, not caring about the events, you should probably stick with the geo viewer or an alternative. Okay. So yeah, now that we've know how to look at the geometry and where it's defined, we just need to know how to change it and make it what we want. So to start with, if you're not a member of the GitHub, it doesn't necessarily matter if you're not a member of the GitHub team, but you'll need to clone the GitHub repository to somewhere new if you haven't already got a local copy. And then build that cloned version of the code. So it's no longer going to be looking at the opt/detector version. It's going to go into your newly compiled version of this code. So to do this, clone and then cd into the Epic repository. And then if you ls in there, it's got a bunch of folders, directories, including that macro directory, which we didn't previously have access to. And then you can cmake -b tells you where the build is going to build it into, and then sourcing from the current directory and then installing into install. And then that actually does the build and the install. Get this comment that you can speed it up by adding this -j4 command. And then you'll want to, after that, you want to source this install setup.shell rather than the /opt/detector/setup.shell. So this is essential for the next part of the tutorial, that you've got this local install so we can make modifications to the XML and the source code and check what happens. So the exercise is, install this, download this, install it, and verify that this detector path now points to your correct location. And then again, trying to export the DD web display so that it's trying to export from this correct path. Make sure that it's still able to do that. Again, if anyone runs into problems, please speak up and we can try and solve those. Some of you probably already have this installed locally if you've been making small changes, but So it does take a while to build if you don't add that J. Depends how many cores your machine has, obviously, as to how high that J can go. So yeah, might take a while. So I'll carry on if anyone's waiting for that to compile. I'll talk a bit about the anatomy of this detector plugin. So we now know what's in the XML file and how it's been parameterized, but yeah, this is the point that we're trying to work out, how the code actually knows what to build from that parameterization. So for this, we're just going to look at this epic vertex only.xml configuration. So this is part of the question earlier, was how does it know what detector, which source code builds what detector? And this is linked from this epic underscore vertex barrel, which was in the need to bring this down. So in the type of this detector block that we're trying to build. So in order to locate where this is actually sourced, we can use this convenient grep underscore dash r epic vertex barrel in the source directory, and then it comes up with this nice line which tells you in the barrel tracker with frame underscore geo.cpp file, there's this declared det element epic underscore barrel vertex barrel, and then so that's the needs to be equivalent to this type in the detector here, and then the other part, this create barrel tracker with frame, is now a function within this detector CPP file, which I've opened earlier. So create barrel tracker.frame, so that it knows which detector to build with which function. No questions still? Yeah, so now changing the contents of this will obviously change the contents, change what we're actually building from this detector. So we want to know how this is controlled from the XML file first. We need to bring up sort of both of these files side by side is probably the most useful way to go about this. But within this, the source file, you'll see a number of different different parameters, such as this description, which contains the whole description of the detector that's being built, and this E, which contains the whole description of the detector that you're trying to build, the XML description. So for instance, this description has a subcomponent called air, which is a material, which is then previously defined in the materials.xml file. You got a question?
Yeah,
Okay.
sorry. Why not to name them the same XML file and source file?
So that's just that they could be, but they don't need to be. Maybe it's something that should be pushed and suggested
because it will create
to make
chaos
this
a bit chaotic.
Yeah, the issue with this in particular one is that you could call this function with 5 different detector types.
But XML is not connected with system.
So I haven't looked into too detailed whether any of these other detector types actually call this, but there are obviously historic reasons why this has been kept in.
Is this a suggestion to name the same?
Yeah. So the top one here is obviously the same as the name of the file, but the one that's being used currently, vertex barrel, is not the same as the name of the file. So one of them was once upon a time.
But I'm talking about XML file, not CPP.
Oh, the XML file itself. Yeah, again, it probably will be worth having some consistency.
Yes.
In the.
It was very confusing for me at first.
Okay. My suggestion is learn to play with grep. To find things, use grep if you're getting lost. If you can't find something that you'll think that you should be able to find. Or in VS Code, you can often control click on things and it will magically bring you to where you're wanting to go. Okay. So back to, so this description contains, for instance, all of the top level parameters, top level descriptions of like the materials and any high level constants that have been defined. So you can grab stuff like air, materials from there, or you can put, I think you can grab anything from there, but you might have to go through a big hierarchy of names and detectors in order to get to where you're going. Whereas the E just contains what you've got within this detector block here. Contains all of that. So this E has been then passed as this XML underscore det underscore T, which is the type that is being interpreted as, which has a particular set of parameters which it should know, it needs to have, and additional set of parameters that it could have. So for instance, you've got the air here, and then you've got this detector ID. It knows how to interpret detector ID and the name based on just these helper functions, which obviously not everything will have a helper function predefined. I've given a link to a list which exists there, but you might more often want to define your own name, or you don't want to rely on this helper function existing. So in order to access these things, you'll need to use this. There's a couple of different methods you can use, but there's this get attribute or default, which passes, in this case, the X support, which is a sub bit of the XML description, and then looks for a thickness parameter within that XML block.
But it's maybe better to show this particular lines from XML block, as I say. And
so this doesn't actually exist in. Okay, there's a separate example which would be more useful, I think, but I didn't get a chance to go back and change that. So you've got a module, and the module has layer materials here, and then you've got in here, you can find the module. So this loops over the modules, and then you've got layer materials in here.
Can I comment on that as well? So at first it was very frustrating for me to get to know how things works here. And maybe it was worth, why would we have such a strange loops? Why do we have XML collections and compositions, and what's just an addition to that particular page you have? Because
So what's
well, I'm not used to. I have a lot of C++ experience, but I'm not used to XML collections, to this strange loops. It's a bit strange.
so these loops are just, they're looping over.
Yeah, I know, but for the first time reader, they're absolutely frustrating.
Yeah, so it's effectively, I guess, a vector of modules. This would be looping over, for instance, you've got a vector of, let's look in this XML file. You've got the detector here, and then within this detector block, which the main detector block ends there, but then you've got, this goes all the way down, contains everything down to this detector closing block. Within this detector block, we've got, for instance, this some sub-blocks called modules, and there are 3 of those. What the code find this
and
again.
Is there a manual for all of that? Because who has written it first should have written some documentation.
Probably expand this tutorial to be a bit more.
Yeah, this is my suggestion only.
A bit more detailed on this side of things.
As I've struggled with it a lot. Okay,
again, how much detail you can go into in these sessions. But yeah, if there are confusing things in particular that people have struggled with before, then yeah, it would be useful to know this and go into these more details. So yeah, so this one loops over any subcomponents of the detector. So it's passing in this detector, which is xdet, and looping over anything, any sub blocks with the Unicode value of module within that detector. So here we've got this. Okay.
Just a question. Just wondering if the SU stands for, is that for sub or something like that?
I didn't myself develop this.
Okay.
Where was the SU?
Oh, it's the.
Oh, on the,
okay,
so
loop.
probably support unit or support. Yeah, it's just an iterator in this instance, but it's relating to that support. And then it's been changed into. I can't comment on why we always.
Sure, it's just
double define it. That's
just one of those.
Which I
could be named better to be a little bit more self-explanatory. I mean, I get what it is.
Yeah. Okay, so more detailed descriptions on these XML loops. Yeah. So this would loop over all of the support units, but in this description of the vertex barrel, none of those are actually being implemented. So that's perhaps not the most useful description example.
But if you look at the other codes, they're a total mess.
Even more of a mess.
Yeah.
Okay. But why
we should have some, I don't know, guidelines or so.
So someone will have to go back and clean it all up, but are you volunteering?
It's a lot of work.
Yeah.
Yeah, to speak to that a bit, I mean, I was doing a bit of this with the pair spectrometer recently, where modifying these things, looking at them for the first time is a mess. And I think the problem is that, perhaps there are some older descriptions floating around. Things are kept to a relatively uniform scheme, I think, and people try to stick to a certain scheme of them. But I think starting from scratch would be intimidating, but a lot of the time it is a case of something exists and it's finding which one exists and modifying it. And, it is a confusing mess. And even for the detectors I work with, it's confusing. But just playing around with it and doing a bit of trial and error is the kind of, that's why I found it useful. diving in, sorting and changing the parameters. You send things flying off into space, but that's the only way to find out what parameter actually controls that, right?
Okay. Or just clean up the code so that nobody runs into these these problems. But all of these, yes, I think this is, the XML interface itself is confusing itself. The XML underscore call. I don't think there's good documentation that I know of which helps you understand the difference between these XML columns, XML detectors, XML. It might be out there, but
it's no less painful than defining geometry in Geont is anyway. To be honest, that alone is a weird sort of doc art. To be honest.
Okay. So back to this briefly. So this will get a from this particular block that has been identified in this loop of support blocks. It will try and locate something called length, and if it finds that, it will pass it as a double to this support underscore length. If it doesn't find that in the block, it'll give it a default value of 2 millimeters. There's some arguments, I guess, where we shouldn't even be considering passing default values. Everything should be well defined in the XML so that you can locate it. But for certain aspects, it's useful to keep it.
Can you show how to add a new variable into XML document so I can read it in my C++ file?
So this is the exercise that you'll
Good, thanks.
Try and do in a minute. So the exercise now is to, you don't necessarily need to check out a new branch, but if you want to keep your main fork clean, or you can always revert back to that. If you're not familiar with Git, then ignore this first step here. And then I want you to try and add a new configuration parameter into this compact tracking vertex barrel XML somewhere within here, and then add a print statement within the source code, which will print out its value. And then you'll have to recompile, and then you can either run it with the DD web display that reloads the geometry, that has to load the geometry, so it has to run the source code, or you can, that's the best way of doing it. So this might take a while, and please reach out if you don't know what you're doing and have additional questions or struggle with some of the syntax in either the CPP file or the XML file. There's plenty of help here and online. I'll give a demonstration afterwards.
Sure.
give everyone 12 minutes, maybe 15 minutes for doing this. If anyone has a working solution and wants to share their screen to run everyone through it, then call out or post a screenshot to the Mattermost.
Sorry, can I ask? So I go to XML file. I go to the detector description where it's like opening, and then I found there are some modules. So should I add the constant in the modules in the detector?
You can choose where to add this. So if you add it inside a module, you'll have to add your
in the loop of the modules.
print statement inside the module loop. If you add it just inside the detector, you'll need to add your print statement in the detector part of the code.
should I use only Unicode variables? Those which are defined in this Unicode list? Or can I create my own?
Then
New
underscore
attribute.
U will interpret whatever's inside as a Unicode
Yes,
variable.
but yeah, but it's I have an error. It's not a member of the differ help slash double dot XML.
Do you want to share that, or should I come down and?
You can do it yourself here.
Oh, okay. I'll see
You
if
will
this works.
go to the same mistake.
Okay.
Good question. I can't answer it off the top of my head.
So you have the same problem. Exactly the same problem.
Um, forget the reason why they're all. No, they're not
It's
all.
not defined in the Unicode namespace of DD4
Did I mean? What did it say?
You can use, for example, info instead of new attribute or some other.
So there are some which do that you. Didn't think there was a list of these somewhere, but
Or property.
First thing you do is, it usually
I was pretty sure you could name them anything, but maybe it needs to be something else then. Maybe it is just you. It's the specific. Okay, let's stick to the ones that are included in this list here for now. double check what I've done previously. That's not even working. Forget to save. Double underscore. Okay. Now just it's very strict about you needing to use the attributes that you're to variables that you're defining.
But it's a string. You cannot really. Okay. I had a problem with the string variables. Undefined reference. Has anyone online done that?
Anyone online want to speak up or? We lost you all. I just got very lucky in my previous names of. Nope, wall doesn't exist, but this one does work. Ah. Is everyone online okay? Has anyone got any questions, comments, struggling with these details?
I would like to comment on your page. So in your exercise, you should also source the detector because it's
Okay.
not written here, and some people can
Yeah, okay. So
which are not haven't sourced their detector setup. They will source this default one, and there is no changes in the default one. So in your tutorial, please add source instruction. There's nothing about it. Yes, here.
okay, so there was part of this bit before, but not.
But if someone decides to go exactly through this instruction and they haven't done previous steps,
Yeah.
and
Okay, we need to source the correct detector.
exactly, yes.
Yeah. Do you manage to get something working, or is that still the problem with sourcing?
And I have problems with the array of chars characters. It doesn't want to allow me to pass this array of characters.
An array of characters to.
Yeah, only specifically encoded in this Unicode properties of variables.
Yeah, so it might be something to do with this XML_comp requiring only specific. I don't know, because I've used that for other names before. Since there's frame, I don't know if frame's part of the. Okay, frame is the. Yeah. Anyway, okay. So, let's move on from this bit. So what I did here was define something called config in these two modules, but not this third module. So we've got two parameters called config added to this module block. Let's start here. And then if we search, go back to config. And then within this loop over the modules, I have this double new attribute, new at called, which grabs the Unicode config from the module blocks. If it doesn't find it, it gives it a value of 2 millimeters. And then it simply just cout statement after that in order to print it to the terminal. Now, if you run this web display with the export, you get 3 modules, well, 3 values output to the terminal. You've got the first one that it comes across, 10.5, another one, 12.5, and then the third one, it doesn't have a value, so it reverts to the default value for the third loop over this modules block, which is this 2 millimeters, but the, well, 2 times millimeters, and the internal units for the DD4 HEP convert that into centimeters. So that's 0.2 centimeters. Right. Hopefully, if you haven't managed to do this yourself, you can come back to it with an idea of what's going on. I will look into the different Unicode problems that we've come across just now. So that's okay for configuring detectors. But if we want to actually build new detectors components, we need to learn a bit more about the geometries and how the geometries are defined in DD4 HEP. It's quite a similar way to Geom4. If most people might be familiar with that, where you've got a shape. The shape is given some parameters like the volume, the material, and what you want to do a charged particle interacts with it, or any particle interacts with it. And then that's given a volume. And then this volume is placed somewhere in the geometry. This can either be inside the whole detector volume or within a sub-detector volume. So you can nest volumes inside each other by placing them in there. So just start by looking at the shapes and volumes. Most common shapes, you're likely to find a box and boxes and tubes. These relate well to how we build detectors. So for instance, tracking layers are effectively a big tube, but they could be a big tube built up of flat box-shaped detectors going round in a circle. So if we look inside barrel tracker with frame geo.cpp again, let's bring these over here. Close that one. Can find examples of both on these lines of the code, so 172 and 173, which will be moved now, maybe because of. So here we've got a box and example of a box shape which is being converted and used as a volume. So here the box is being given a width, a length, and a thickness, which conventionally are half width, half lengths, and half thicknesses for various reasons. And then this is being converted into a volume with a name, being passed the box shape, and then being given a material which has been passed in as a parameter to the XML. So this X.
Sorry.
Okay.
Just to clarify, this half width because you define the center of the
Yeah.
volume. This is why, not some other reasons.
Yeah. Okay. You're placing the center, so you're wanting to define the size outside of the center. So these layers. So in this, so these boxes are later put inside module components, which are described as tubes. But this module component is given material of air, so it's placing these boxes with these materials, which are defined in the XML, into a tube volume, which is just air, which is the same as the environment of the entire mother world volume. So this is defined slightly further down. So you've got these tubes and volumes defined here. And then you can just building the layers. So you've got the layer is a tube, and then you're placing slightly further down, placing the volumes of these detectors inside of these tubes, these tube volumes. In DD4HEP, there's also this volume called an assembly, which is just a group of different boxes or different volumes, which has been placed within a volume relative to each other, but without necessarily any properties of its own. This is quite convenient for nesting things together, which Geomp4 sometimes has some problems if you're wanting to create a mother volume to contain a number of certain smaller volumes. You need to have some very complicated Boolean shapes, whereas in DD4HEP at least, and TRootGeo, you can have these assemblies, which are just mean that you can place all of this inside of the mother volume, and then it works out the boundary boxes for all of these smaller volumes within that bigger volume. Yeah. So if you know the names of, or want to see some of the geometries that the shapes that you can produce, they're defined through these links. You've got these different shapes defined. The DD4HEP manual doesn't give some nice pictures. The root manual does give some nice pictures of help you decide if the shape is correct for what you're wanting to do. And then if you're not sure how that converts to a Geomp4 volume, there's probably a better description of this, but there's an old issue on GitHub which has a nice table which has like the 3 columns: Geomp4 geometry name, TGO name, and DD4HEP name. Yeah. So there's also some very simple geometries that you can build without a CPP file defining them directly. So they have some shapes which can be defined straight from the XML, some inbuilt CPP to the DD4HEP core libraries. But I don't think we use those very much, but you can just, if you want to just define a tube with a material and placement, then you can do that. But if you want to define anything more complex than that, you're going to have to write your own CPP value, CPP file. So it's going to suggest try and just create a new volume within this barrel with a frame and see if you can visualize it using the DD web display again. So for instance, create a new box and place it somewhere in the volume. It doesn't matter where, it doesn't matter what size, as long as you think you'll be able to see it when you visualize it. Yeah, and then you could do it by producing a new tube, which contains all of the 3 other tracking layers, which are in this geometry.
Shouldn't there be some discussion about mother volumes and volumes? To which mother volume should one put and so on? It's quite a complicated topic, I would say.
So I didn't actually write anything about placements, positions. Yeah, so when so you've got these volumes, but I never wrote the section about placements. It's not placement, it's just so you can get started with the definition of this while I try and get an example up.
Yeah, this placed volume.
Yeah. So here's an example where you're placing the layer volume, which has been produced on the right here, with a layer position. So you're passing it a volume and a position or some translation relative to the center of a mother volume. So in this case, there's a mother volume described as assembly, and you're placing the layer volume relative to that, at this position. Yeah, so you need to place volume, assembly, place, or whatever volume, place volume. So this assembly then gets placed inside of this mother volume, which is defined as the stet. And then you'll.
And physical ID. But this is for sensitive, I guess. Yeah.
Yeah, so that's for the readout. You don't need to worry about the physical volume ID at this moment. So I'll try and do this in real time as well. So just. Layer position.
And what happens if I put a bigger volume inside the small mother volume? It would give me overlaps and also so layer inside each. Should it be placed inside layer? Small place tubes, or should you place them inside this big detector mother volume?
So I'd recommend placing this in the mother volume so that it can contain in the world volume.
World volume. Okay.
So that will be this.
Yeah. Maybe it's lacking here. What is world volume and so on.
Yeah. No, this is. Please do. Success? No? Oh, do you want to share your geometry visualization, Adler? If I can work out how to stop sharing, I've lost my. Do you know how to get the zoom controls up if you've lost the zoom controls?
Up there.
If you hid them on your laptop, like, yeah, I could force myself to stop sharing the screen. Share my own screen and then stop share. Okay. I hit the controls on my laptop and I couldn't work out.
Okay.
Get them back again. That seemed to work.
But then Sasha, you're going to share?
Oh, you're not going to share
Oh, you
share
can
your
share.
screen. And then you can.
I'm sorry, I will share.
Good, good.
Yeah.
It's better for the recording, I think, actually. The screen will be recorded.
So, okay. So what I've done, I have this tube, lay tube. The detector parameter doesn't work, so I've put it manually to some numbers. Then I also there have a like in the name, the string name, and I placed it here with this command set this volume, this particular layer volume, and then I compiled it, successfully compiled. So I had to debug a little, then install, and it worked. Many problems actually. I can show you. I will make a comment, maybe a better descriptive of what is lacking also.
So on the visualizer there, can you now hide the volume that you made so you can see the
Yeah, I guess so.
see the volume behind it?
Okay, it's not here.
So if you just right click on it on the and then,
Yes, this is my layer. Actually.
and then
So this is-
hide.
Okay, here is the detector.
There, yeah.
Yeah, you're right.
Good.
Okay, so that's it. Thanks.
Okay, in the last few minutes before I hand over to Nathan, I think just run over the overlapping section so you can check to see if what you've just created overlaps with the other volumes, or if it doesn't, and then if it doesn't, then try and make it overlap, or if it does, try and stop it from overlapping. So this is a script which is run in the continuous integration of on GitHub. Every time a new geometry is suggested to the repository, it needs to check that you haven't caused some horrible overlapping geometries. Your boxes don't want to interact with each other because otherwise a geometry particle in Geont4 doesn't know which material it's passing through or where the boundary between it and the next geometry box is. So in your EAC shell, you should just be able to run this command and see have a look at the output from that. That's good. That's good. Might take a little while because it has to check quite a lot of points. Yeah. there is another section down below about how to define the readout for your detectors, but we obviously won't have time to cover that section. I think it only, yeah, okay. Because I've not managed to compile mine properly. Okay, so for instance here, if you look back up through here, it's checking different bits of geometry. It's successfully built the geometry. And then I believe that this output doesn't contain any overlaps. I'd have to do the web display, check that quickly myself by eye as well. Has it gone? Yeah, so obviously that tiny little, the original trackers are not being overlapped by this big geometry here. But if then you were to change change your geometry so that it's got a starts at an inner radius of 0, it should definitely overlap because it's got the same center as the detector that's already there. So I hope, yeah, so we've now got a failure of the overlap. It's tells you which volumes are overlapping and says overlap with volume already placed. This particular volume is overlapping with this vertex layer 2 is overlapping with this vertex overlapping with big tube, which is what I called my new detector volume. So that gives you some idea if you're building a new detector, where it's overlapping and what's going wrong, where you need to look. Okay, so I think that's my time for today. Hope everyone's learned something about the geometry building, at least, and not caused any extra confusion over what was already there. and there's some material to go back over if you're wanting to have another look, or email or get in touch over Mattermost if there's some problems later down the line. Some of the material will be slightly edited given the feedback this session.